here, right? I know my limits on this height. But so anyway, I want to start by showing my email address down here. Because I gather someone tried to email me and it was written something like media@anl.gov. But anyway, this will directly get to me if you want to contact me. So I'm going to continue what I was talking about before on things that you can really only do with these very high intensity X-ray FPLs. And one of the things that you really can only do with such a source are doing some stimulated emission studies because of the very high power. You can do a shade decay rate and to actually make high population inversions so that you can actually make atomic X-ray lasers. And those are pretty prominent in the field, and so I want to make sure you guys know about them because I think they're a little bit special. Okay, now also reacting to another comment that I had, like, oh, Argonne, I thought that's like Krypton, or Superman was born or something like that. But Argonne, when I say Argonne, I actually mean Argonne National Lab, where I work. And Argonne National Lab is actually the very first DOE laboratory. It was founded by Enrico Fermi, actually. And it's a multidisciplinary lab that has two very large world-class facilities. One of the large world-class facilities it has is the APS synchrotron, which you've heard mentioned before, and where I work, and also the high-performance computing and data center. So, in accordance with Hussein's very large interest in Moore's law for X-ray sources and for computers, I showed this graph, which actually, besides showing, generic ones, it shows some that actually exist at Argonne. So this is why we particularly have this graph, right? And so what it shows is this third generation synchrotron APS here is an Argonne thing. And the other thing that is an Argonne thing is this IBM Blue Gene computer. And so let me just say this.
Can I ask a question? Where would the power book be on your computer curve?
Oh, okay. So we can figure this out together. Computer speed in megaflops, millions of operations per second. Right. So I guess that would be 10 to, it would be like a gigahertz, right? So 1 gigahertz. So that would be like here. Okay. 10 to the 1.
So it's the same as $1 million computer 50 years ago?
Yeah, right. I guess that's similar to this IBM 790, right, in 1960. That was the fastest in the world. Yeah. So what's, okay, so these X-ray sources are really fast, right? And the computers are advancing maybe not quite as fast. And at Argonne, we have this thing, the Mira, which runs at 10 petaflops, and it's the 5th fastest computer in the world. And then in 2018, there's going to be this Aurora, which will run at whatever, 180 petaflops. Pierre's shaking his head. No one wants that much computing power. But okay, so those are the two new things.
What does this name mean? Advanced Leadership Computing Facility.
Oh, well, everything has to have a name in Argonne. And so this is a facility, just like, it's just a name for it. And it has more than just this Mira computer in it. It has other slightly smaller computers, but it's something that encompasses the Mira and a couple of other.
I think it is leadership.
Oh, you don't like it? I see you don't like it.
It sounds difficult. It's difficult for me to understand in this context.
Yeah, I guess it's just a name because it's not the fastest in the world, right? But it's always been called this. Right? So for Argonne, it's the leadership computer facility. Maybe not for the whole world. Right?
I mean, the fastest computer right now is Chinese.
Yes, right. It's this Chinese
running
thing
is
in
about
Shanghai.
50-some petaflops, right?
Yes, I think that's right. So anyway, Well, everyone wants to go to X of something, right? I think Phil was telling me that they want to go to exawatts in Europe. It's a, you know, so anyway, so this is that. So this is the advanced photon source, and this is this supplies very hard X-rays with very high brilliance to roughly 100 experiments simultaneously. In 2014, there are about 6,000 users doing all kinds of different experiments. And shortly, just like the computer will evolve to something, this will also evolve to an upgraded APS, where it will be about 1,000 times brighter. And basically what's going to happen when it evolves and gets 1,000 times brighter is the APS today, I think Bill described bending magnets, he described undulators, et cetera. But the APS today, the actual X-ray line that comes out is a little bit elongated in one direction. But by changing the lattice of the APS, you can actually make a round beam coming out. And so with that, the brightness is basically the flux divided by the spot size and the divergence. When your spot size and divergence go way down, your brightness goes way up. And the way they plan to do this is this multi-bend achromat lattice concept, which is actually now being pioneered in Sweden, in Lund, in Max 4, where they're actually, they've already built it and they're going to commission it on Midsummer's Night of this year, June 21st. So they're doing proof of principle now. And the whole idea is that this whole wide horizontal emittance can be concentrated by just slowing down the bends around that circle. And so the emittance in that X direction is given by circumference times the beam energy divided by the number of these dipoles that go around. And the idea is to have like 7 dipoles, whereas now we have 2. And so that's really going to decrease a lot. But in order to do this, as you can see, this nice picture shows this is how you have now. So you have to actually fit inside that large structure this new set of magnets and insertion devices and so on and so forth. So, you know, it's a big project, but presumably at the end you're going to have something that's basically the ultimate 3D microscope. And it will have the very high energy. It'll go up to 100 kilovolts. It'll enable you to penetrate bulk materials and operating systems. Remember how Margaret was having problems going through, you know, a few nanometers of stuff? But with this, you can really start to look at things in action. It'll have the very high brightness, and so you can really start to scan things very reproducibly and over large scales. And it'll have very high coherence because it's this nice bright spot. And because of that, you'll be able to do some of that lensless imaging that Margaret talked about over here also. And there's a big program to be able to do that. And so the different, you know, so these are user facilities. You just apply for beam time, and then you come if you want to do some experiments there. And so this is for Pierre, because he was so interested in this particular picture. This is fluorescence tomography that's done at the APS of a diatom. And there's this cute little movie that shows, you know, all the different elements inside this diatom. This is something that's found in the ocean and does a lot of pickup of carbon dioxide. And so you can actually quantitatively determine all the different elements inside, you know, this structure. And it's, you know, you don't need the infinite resolution for these things, but it's very nice to just shine your X-ray on and see all the elements just from their emission and localize them very nicely. And this movie is actually available in this particular paper in their supplemental materials if you want to see it. Okay. So because of all these things that you can do, there's a real worldwide march to these sorts of technologies. As I mentioned, the very first one is coming up this year, Max 4 in Sweden. The next one planned to come up is in Brazil. And then there's a sister facility to ours, ESRF in France, that's planned for around 2020. And then the APSU, where you have to, you know, the whole circumference of the ring is 1.1 kilometers, so you have to remove everything in there and put it all new, and that's around 2022. So, these are things that are coming down the line. All right. So now back to AMO. After telling you what's at Argonne. So if anyone wants to come visit, it's also right outside Chicago, and so there are lots of interesting things to see. So this is kind of the thrust of what we like to do at FELs. And I talked about the fundamental nature of X-ray damage at high intensities earlier in the other sort of talks. And what I want to focus today on is sort of more, can we actually really start to control intershell processes? Because now we have, the intensity from the XFEL that might enable us to do that. And so we of course started right away with this because we thought it was very exciting, right? And so, real early on at the LCLF, we thought, oh, let's look at X-ray processes at high intensity. And this was a nice collaboration with our group, and also, Phil was involved, and Lou DeMauro, and other people, and it was really fun. So, everything I told you about before, really, we weren't trying to get resonance. Now we're actually trying to do something with the resonances, right? And so what we thought is, okay, well, we sort of understand how things go, right? Let's say if we look a little bit more carefully at the edge near neon, what you see is this very nice Rydberg series. So you see the 1s to 3, we're always looking at neon, 1s to 3p, 4p, etc., out into the continuum. So we thought, well, gosh, we have all this high power from the FEL. Can we actually start to induce Rabi flopping? And so you can do a very quick back of the envelope calculation, saying, okay, well, we know the dipole matrix element for that transition, we know the lifetime, we can calculate what intensity we need to do to cycle, the population up and back. We calculate, oh, well, we only need on the order of 10 to the 18 watts per square centimeter. And, I kept telling you that we were going to get up to 10 to the 22 or 10 to the 18. Okay, well, why don't we try it and see what else could happen, right? And so if you look at what happens, let's say you do this 1s to 3p transition as shown in this upper figure, what's going to happen with the next photon that comes in, right? Well, it's pretty unlikely that that 3p is going to go out into the continuum. Remember all those cross-sections. I mean, yes, the cross-section way that we think about things. And it's also pretty unlikely that you're going to eject this 2s electron. But what's incredibly likely is that that 3p is going to be driven right back down to its ground state, because look at the size of that cross-section relative to anything in the background. I mean, that's the thing that is likely to happen, right? But the LCLS line width was on the order of 8 eV, which is not so conducive because the line width here is on the order of 1/4 of an eV, right? So it's not as if you have, it's not necessarily the most advantageous conditions. Well, but this wasn't the first experiment. We'd already learned that we could actually, manipulate the neon atom a little bit. We knew that early in the pulse, if you were below the ionization threshold, you talk to the valence electrons. So you can actually pull out one of these 2p electrons, and you can actually, instead of doing the 1s to 3p, you can actually do the 1s to 2p transition and cycle that one instead. That has some advantages. So one of the advantages is that the cross-section for that particular transition is, well, it's way higher than going out in the continuum, but it's also considerably stronger than the 1s to 3p. So we figured, okay, well, why don't we do that? Why don't we use the early part of the pulse to prepare our neon atom into this state such that we can do the Rabi flopping on that? So, and how would you what signature would you actually have for this? Well, before we did the experiment, we had this nice theory by Nina Goringer and Robin Sandra saying, okay, well, if we do this, what we can do is we can, expect a change in the shape of the resonance chamber. And so they calculated for a single shot. Remember, these are ugly pulses. And so for a single shot, you can look at what you would see for this SASE, for the resonant Auger line. And, oops. Now, why did it do that? Okay. And of course, it's very hard to see what would happen there, but you actually can look for, an average over 10,000 shots, because you don't really, you aren't seeing you don't get an entire yield from one shot. And you can look at the difference for when you have a very high intensity versus a lower intensity. What you can see is that at high intensity, you have a broadening of the Auger line relative to the lower intensity. And that would be your signature of the Rabi flow. So we thought, okay, well, we'll look for that, right? And so what do you actually do? So you start, okay, what this graph shows is the X-ray energy down here scanning up from 840 to 860 eV. Remember, the actual threshold is at 870 eV, so all this is below threshold. So you should not actually see any Auger at all, because the only reason you see an Auger is if you've made a hole if you've made a hole in 1s squared. So what you see is, if you make your pulses short, if you don't make them long so that you ionize all your valence electrons, you can make them short, tune them to this energy, and look for this. So the very first, early in the pulse, the first photon, what it does is it ejects out a 2p electron, and this is what you see, down at below the 1s threshold. And then as you start scanning up, when you actually hit this resonance, then you start to see the Augers coming up. So this is at this 1s to 2p resonance, right? And so what you look for as you scan across that resonance is that you look for that to broaden. So it'd be nice if this thing looked like a little diamond when you actually hit the resonance, but at this point it sort of looks like a line. So that's the absorption of the second photon after you've already created that hole. Okay. So then you have to look rather carefully. Okay, well, is that line broadened when you hit resonance? Well, first you have to determine, what that line looks like when you're off resonance. And so you can easily do that by putting your photon energy above everything, right? You can get a line look for that, and that's this line shape there. And then you can go down to the place where you can tune your X-ray energy to where you're on resonance, and you can see the blue lines here. And you can see that there's a small difference. It's slightly broader, right, as expected. But I would have to say, I'd have to admit that it's not, it's not like, oh, for sure, it's not so obvious. If you deconvolve all the instrumental and other line shape issues associated with that, and just pull out what the theory is, then you can see over here that the non-resonant versus the resonant, you can see that there's a broadening of the wings. Okay, so that's kind of the evidence. And why is it so small, right? I mean, it looked much broader in the calculation. Well, the calculation, like it would be a much more significant effect. Well, the calculation actually showed that it was for one intensity, it wasn't volume averaged, and it was also, right, it's always this issue, and it was also for 1s to 3p as opposed to 1s to 2p. And the 1s to 2p actually has some dynamics going on before you actually do the resonance, right? And so you can see that the actual occupation for the 2p naught in this red never goes above like a couple percent. So the actual coherence that you have for the system is not as high as you would, of course, if it were a really nice pulse. And so this is sort of the simulated Sassy pulse, and this is the coupling between 1s and 2p. And so the Sassy, right, what you expect for the Sassy line width is shown here. But if you had a nice pulse, a nice Gaussian pulse, then you can also calculate what you would see. And of course, that would be a whole lot better. It would be much more obvious as to what you would be looking for. Okay, so then what do you want? You obviously want to do something better than your Sassy pulses. And this is, you know, Phil told you about some of these things, and I'm just going to tell you a little bit more. Because there's more than one way to do this. There's the self-seeding that Phil told you about, but there's also these atomic X-ray lasers that I want to tell you about also. Okay, so Phil showed you this slide already, and I guess I don't want to repeat what he said, but I think I have a little bit, okay, I have a little bit of, you know, some entertaining personal stuff that goes along with this. So this diamond isn't the real diamond that you actually just buy get from some manufacturer. It was actually, and that particular cut was made by this Russian institute, the Institute for Super Hard Novel Carbon Materials. And they have a design, they have a program just to make novel carbon materials, right? And there was a nice collaboration because there was a person in there are a bunch of people in our lab who are also really interested in making this particular thing go. And Phil showed you this when the diamond was out. You have this very broad bandwidth, and when the diamond was in, such that you would create this nice little seed, and then you'd overlap it with the electron beam, that you'd have this very nice line. But you know, there were issues, right? It did not actually achieve saturation. It was a great demonstration, and the power data is still present. But you know, one of the other issues is we actually went to do an experiment just to test the difference of how these two types of pulses would act in different systems, and there wasn't actually a diagnostic for this downstream of the experiment. If you do it upstream of the experiment, you kind of lose your intensity, so sometimes that's not the best. Okay, so this is actually a picture of all the guys. I mean, they're so happy after this happens. And I want to point out to you just a couple people. Let's see. So this is Zhurong Huang, who is the real guru of the theory for the FELs that Phil pointed out a couple times. This is Gianluca Geloni and Yevgeny Solomon, who actually came up with this idea for the self-seeding. This guy back here and this guy back, these two folks are the guys who actually made that thin diamond crystal. This is Sasha Zolins from Argonne, who really coordinated the Argonne effort, and the Argonne guys actually built that little spectrometer that holds a diamond crystal that goes into the self-seeding. So there was Sasha and Yuri. I think that may be all in this particular picture. Okay. So actually, not only can you do it in the hard X-ray range with that cute little thin diamond crystal that's only a couple millimeters, you know, in size and 100 microns in thickness. You can also do it in the soft X-ray, but it's a whole lot more complicated because there isn't, you know, a similar monochromator for that. But that's also achieved and in principle usable now.
So is there any worry about blowing the diamond up, or like just diffracts perfectly and you don't have to worry about it, or?
Well, I'm sure that they worried about it, but it's really quite thin, and so there isn't so much absorption in it. I know that they have that problem a lot when they're trying to do silicon monochromators. Thin silicon monochromators, but because the diamond is lower Z, there's less energy absorbed, so they didn't have that problem. But okay, so now they're, you know, of course atomic physicists want to have nice seeded pulses, and they want to do spectroscopy and all these other things. But it's pretty tricky to convince these guys who just want to blow up their nanocrystals that they might like to have a seeded beam, right? But one thing that could be useful is that it is a way to get to a terawatt FEL. So right now, the FELs are operating at about 30 gigawatts. But in fact, that didn't actually get you to that super high intensity quite yet, right? And so they might actually like to have more poop. And this is one way to do it. And the way to do it is exactly what Phil was discussing earlier. And what's useful is that because now you have a very well-defined energy which you're trying to match with the undulator, you can actually taper this undulator very, very well and continue to extract the energy out past what might normally be the saturation. So you might actually get some folks a little more interested, I think, in this also. Okay, so now the other way that you can get, you know, a stable X-ray beam to work with is not to use the FEL, but to use an atomic line, just like they did originally with, you know, with the ruby laser. Probably you've worked on this. No, yeah, okay, you know, okay. And so that might be nice, but the reason that people haven't been although there have been lots of attempts, it's tricky. The reason it's tricky is what you want to do for this X-ray rate. Well, of course, for any laser, you want to have a population inversion given by this expression. And then you need a gain to make a laser, and the gain is given by this expression, which, you know, has an Einstein A coefficient, a wavelength, and a natural line width. And when you put all these things together, you get that the gain is, you know, is proportional to this expression that goes as lambda squared. And remember, lambda is going down when you're going out into the X-ray range. And so then the required pump power density to compensate for the level depletion ends up going as this expression, which goes to lambda to the -3. And then the pumping power to maintain a particular gain goes as lambda to the -5. So the amount of power that you need to make this, to keep this population inversion is huge, right? So people had lots of ways, because they wanted to make X-ray lasers, they had lots of ways to do it, including these nuclear explosion pump lasers in this Star Wars era. I remember, I think, well, anyway, I know Phil knows about it, right? And I think Ken Schaefer might have even been in Liverpool when this was happening. But there are, if you actually want to read about it, you can read about it in some of these references. But the whole point, how are they going to do this? The whole point was they wanted to create population inversion in a very hot, dense plasma. And the way they would produce it, well, typically would be an optical laser, but also maybe a nuclear explosion. And the idea was that you have lasing in these outer shells, and that you could deplete this lower level very rapidly by a fast radiative decay. But you'd have to really pump up, you know, your system very, very, very high. And so this was achieved at Livermore originally with neon-like selenium, lasing at 20 nanometers, and they had a kilojoule of pump energy, and they focused it down onto this line, and then they looked at the radiation coming out on either side, and they could see it. Okay, so this was, I think, a very huge effort, and took a huge laser. Remember, it had the kilojoule of pump energy, and so this was a picture of it. And there are other ways, you know, things have advanced since that point in time. And they've advanced largely from the efforts of Jorge Roca, who was actually, you know, originally that huge thing started out at 20 nanometers with basically a kilojoule of pump energy, a huge effort. But he's been able to get it down to a pump energy of around 4 joules. And he's been able to do this by having sort of a grazing incidence pumping scheme rather than just flat on. But it's pretty amazing, right? You know, now he has something in his lab that can go down to 7 nanometers, which is pretty short, right? And it's something that you can envision, you know, going and using if you want to, even at fairly high rec rate. And in this reference, there's a lot of information on that. But then, right, there's another way that was, in fact, proposed back in 1967 by Duguay and Redzepis in this paper. And what they proposed was something that is pretty obvious now, that you can actually eject, you know, 1s electrons or whatever, and actually directly create a population inversion. And he suggested both for a sodium laser at 30 eV, and also a hard X-ray copper laser at 8 kV. And it's this concept that, that Nina Rohr